Hello everyone, my name is Munib and I will be presenting our paper DynaGraph, a dynamic contrastive graph for interpretable multi-label prediction using time series electronic health records data. This paper was written in collaboration with clinicians at the John Radcliffe Hospital in Oxford, and it's sponsored by the University of Oxford Department of Engineering Science. The main motivation behind this project is to help clinicians help patients with heart attack identify complications of heart attack before they occur. So heart attack or myocardial infarction is one of the biggest contributors to global mortality. In intensive care units where heart attack patients get treated, about 16% of the time they suffer one of the following complications: heart failure, arrhythmias, atrial fibrillation, pericarditis, and death. If we can predict for these complications in a multi-label manner at least 1 hour earlier, that will greatly reduce their risk and will help clinicians risk prioritize and direct resources where they're most needed, especially in resource-constrained settings. Overutilization of ICUs will help, addressing that will help direct treatment where it's most needed. So the focus of this paper is to propose exactly a prediction model that will be able to predict risk for these complications temporally. We'll be working with multivariate time series data. So a patient represented as a set of time series features over a span of 10 days in the intensive care unit. Those features can include everything from heart rate, respiratory rate, to blood measurements such as albumin or lactate. Time series are often represented in several ways in machine learning. One is to represent them as summary statistics, so to use variance, standard deviation, means as features in downstream machine learning modeling. Another is to represent a time series as an image using spectrograms or spectral analysis. That's often done with ECGs. And the most common one is to use recurrence models, such as in NLP, with LSTMs and recurrent neural networks to learn the sequential nature, the hidden embeddings of these time series features. Each of these has its strengths and weaknesses. Here we'll be looking at representing the multivariate time series as a graph, particularly a dynamic graph. Static graphs are structural representation of information. They consist of vertices or nodes and edges. Each node will correspond to a feature, and an edge will represent the hidden dependency between those features. Now, that's a static graph. When we have time series, obviously the relationship between the features will change through time, both within and without the features, within and between features. We define a dynamic graph as a series of static graph snapshots where the vertices or nodes or features stay fixed throughout these graph representations, but the nodes will change throughout time. And such, the dynamic graph will be learned in our model. As the model is trained, the dynamic graphs, the weights of the edges will be learnable weights in the model training. This will allow us to capture both the spatial and temporal information of the multivariate time series in a graph representation. And the model that we propose to do this is called DynaGraph. If we imagine a time series over 24 hours, for example, we're going to break it into time blocks of 4 hours each. Each of those time blocks will then be passed through an LSTM to find hidden temporal embeddings of that information for that time slot. Another will pass and be represented through a dynamic graph. When the dynamic graph is constructed, the adjacency matrix, the A matrix representing that graph, is a learnable weight matrix of the model. So again, as the model is training, it's learning how to best construct the graphs considering the downstream task. Once we have the hidden embeddings from the LSTM and the dynamic graph representation for that time slot, they're aggregated together to find to combine both spatial and temporal information in one graph representation G. These graph representations are then augmented to improve performance and to be later used in a contrastive loss calculation. And they're also appended with something called an interpretability weight matrix that will allow us to learn, as the model is training, which parts of the graph contribute the most to the downstream task prediction. In this sense, we kind of add a pseudo attention mechanism on top of the graphs that allows us to make them more interpretable. The core of the DynaGraph is a variational graph autoencoder that is just better at multi-label classification, which is what we're dealing with here. Many of the complications can occur for one patient and we're modeling that as a multi-label classification task. The output of the VGAE is a very complex graph structure, right? So if we have 80 features, that's about 80 nodes. And if we have 10 snapshots, that's 10 graphs, each having 80 nodes and many different combinations of edges. This is a computationally costly weight matrix to compute every time the model is trained and backpropagated through. And so to reduce the computational cost, we use a temporal pooling module that basically says cluster the nodes in the graph to a smaller number of nodes that will contain about similar temporal information without losing too much of that, and greatly reducing the computational cost for model training. Then this reduced graph representation is flattened and given to an MLP for multi-label classification. To comment a bit more on the augmentation interpretations, the augmentations, if anyone's ever worked with contrastive loss, you basically need a negative sample of the original data sample and an augmented sample. In our case, for these graph constructions, our negative sample is just an inverted node vector, a negative inversion of the node vectors, and an augmented one is just a shuffling of the edges for the original graph representation by introducing a random noise matrix on top of the adjacency matrix. We use the cosine similarity to measure the difference between the original and the augmented in the original and negative sample, and use that in the cosine and use that in the contrastive loss computation. For the interpretation, if we imagine the graph, we have another ghost graph or pseudo-intention or saliency map, whatever you want to call it, on top of the graph. So as the model is training, the graph is being updated, right, with the weights it's changing, and it will tell us which nodes and which edges contribute the most to the downstream loss computation. And at the end of the day, once we extract that the pseudo-attention map, it will tell us which parts of the graph are most important. Some challenges we encountered included class imbalance. Severe class imbalance is very common in healthcare applications. We have that within labels and between labels. So for example, for pericarditis, one of our complications, only 0.4% of the patients are positive for it. But also in between labels, pericarditis 0.4%, death 20%. So that's quite a big difference. We use kind of an adjusted focal loss to help us target those small positive examples with higher weightage. To address overfitting, it's a very complex model. We use regularization. Lackluster performance, again, we use contrastive loss because the structural information of the graphs over time does not change as much unless you introduce some kind of augmentation in a similar way you would do that in a computer vision model. And that does help train the model and perform better, as we found. And structural stability, again, if we're looking at a patient stay over 10 days and 4-hour time blocks, the graphs near the end of the stay, near the beginning of the stay, might look very different for no justifiable reason. To guarantee stability of the graph representations through time, again, that they shouldn't deviate too much from each other, we implement a structural loss that will penalize future adjacency or graph representations the more they deviate from the previous time step. In that case, we guarantee stability through time. Our results are highly promising. On 2 real-world electronic health records datasets, namely EIC Mimic3, we show very good balanced accuracy and high sensitivity compared to both time series models, LSTMs, transformers, and dynamic graph models such as graph convolutional networks, GACs, and graph isomorphic networks, etc. As for interpretability, the way we evaluate that is, again, to summarize the contributions in this pseudo-attention map of nodes and edges to the final loss computation. And because we made each of the nodes a representation of the feature, we can then summarize that for each node and normalize it, and get for each feature over time a normalized weight for how much it impacted the final loss computation. And these results have been verified, again, with medical literature and with clinicians that were working with us on this project in intensive care. We can see things like hemoglobin increasing in importance the closer one gets to the event in question, sodium, for example, and all of these are discussed more in the paper. The conclusions are the DynaGraph shows stable results across several multi-label metrics for a severely imbalanced set of complications. for risk prediction of heart attack complications. Our interpretability needs to be worked on more, but it confirms existing clinical knowledge of relevant risk factors, but it's now stratified through time. It allows clinicians to monitor that in real time up to 24 hours into the future. And some limitations that are the computational cost, and pro pooling does help us with that. But again, if we plan to deploy this in intensive care, it needs the training and the deployment needs to be a lot faster, and we need to evaluate further data sets. We have added another data set called the EHR shot, which contains data out of hospital discharge up to a year after hospital. But again, that time frame is a lot different, so we might be looking at a lot more of the structural loss importance there. But yeah, thank you